Next example problem. This one is on capacitors. We have a ladder of capacitance, a network of capacitors with the value shown. Not only are the values shown, there are also some voltages associated with these capacitors. And then they are shown in the figure. What are we supposed to find? With respect to the terminals A and B, what is the equivalent capacitance? C equivalent is what we are supposed to find. And we are also supposed to find the initial voltage across the C equivalent. And here's what we are going to do. We will see that the capacitors in parallel, they simply add as if resistances are in parallel, are in series. Okay, so they behave like series resistances. Similarly, capacitances in series, they behave like resistances in parallel. Okay, so in order to find the C equivalent, we will gradually apply the series and parallel equivalent to every pair of capacitances. And then we will combine this into a complete single capacitance. Now, for the second problem, which is to find the voltage across the C equivalent, what we will simply do is we will apply KVL along this outer perimeter. Okay, we add up all the voltages around the loop, and that gives us the equivalent voltage for the C equivalent, initial voltage. So we'll cross that bridge. For now, let me copy this entire network of capacitances and see if we can simplify this. Okay, so I have this here, 16 in series with 48. When you have two capacitances in series, their equivalent capacitance equals to the product of the capacitances by their sum. Okay, microfarad. Now you can see that because how did I get this? I got this by C1 plus C2 equals to 1 over C equivalent. That is the same as saying the sum of capacitances by the product of their capacitances divided by the sum. This is what you would do for resistors in parallel. Okay, so this comes out to what? 6412 microfarad, if I am correct. Okay, so this comes out to be 12 microfarad. So what I'm going to do is to replace all of the remaining part of the circuit, okay, with one capacitance whose value is 12. Okay, this is 12 microfarad. Now you see the 12 microfarad is in parallel with the 3 microfarad. Okay, the 12 microfarad and 3 microfarad are in parallel. When you have capacitances in parallel, they add. Okay, so I'm going to copy all of this again, duplicate this like so, and instead of this parallel combination, I'm going to have just one equivalent capacitance, which is equals the sum, okay, of 3 and 12. This comes out to be 15 microfarad. Okay, I got that because the capacitances 12 microfarad and 3 microfarad are in parallel. In parallel, capacitances add. Now I have these two in series. Okay, it's a pretty straightforward process from here. I have two capacitances in series. when you have capacitances in series, the C equivalent is what? Is the product of their values by the sum. So that is equal to 10 microfarads. Okay, 10 microfarads. Now I'm going to replace these two orange ones with their equivalent. Okay, let's see. The two orange capacitances can be replaced with just one value, with one capacitor whose value we just calculated. Okay, this is what? 10 microfarads. Okay, 10 microfarads in parallel with another 10 microfarads, like so. So this 10 is in parallel with this 10. So I can replace this. So you see what I'm doing? It's a pretty straightforward process. Once you do it a couple of times, it's actually a silly, easy process. Okay, so this 10 in parallel with the other 10, we're going to add, I'm just going to call this 20 microfarads. Okay, 20 microfarads. Now you see I have a 5 microfarad in series with a 20 microfarad in series with a 4 microfarad. Okay. Now you can do the math. When you have series capacitances, the equivalent C of all the three is equals to 1 over 5 plus 1 over 20 plus 1 over 4 microfarad. Okay. It turns out that this is going to be, microfarad, and this guy is microfarad. Okay, it turns out we can do a least common denominator method, 20 microfarads. Okay, that goes into 5 4 times, it goes into 20 1 times, and it goes into 4 5 times. So we have a total of 10 by 20, 1 over 2 microfarads. This is 1 over C equivalent. Therefore, C equivalent is 2 microfarad. So when you have three of these capacitances in series like this, okay, when you have three of these capacitances in series like this, the equivalent capacitance, final capacitance, C equivalent, is 2 microfarad, okay, between A and B. And that is the solution to part A that we are after, okay? So the C equivalent is 2 microfarads. Now there is a part B to the problem. We have to find the initial voltage, VC initial. Okay, so we have a capacitance like this, which is 2 microfarads between A and B, but we don't know the voltage, the initial voltage between this. How do we do that? I mentioned that we were going to use KCL. Okay, go back to this problem and I will remind you what we are going to do here. Okay, let me copy this and paste it over here. Okay, all the way towards the end of the problem. We are at a point where we are ready to find the VC initial. So all we do is this guy. Okay, around this loop on the perimeter. Okay, around this loop on the perimeter, we find we apply KCL. Okay, we apply KCL and we add up all the voltages. Okay, first is when we are going down this path. Okay, when we are going down this path, we hit a plus and minus first, so plus 5 volts. Okay, then we have another plus 10 volts. And then we have another negative 20 volts. So we are going to complete the path. Negative 20 volts, followed by 0 plus another 30 volts. Okay, once we do that, we're going to see that this is um, 45 minus 20. So VAB is really plus 25 volts. So you see what I have done? I have summed all the voltages along the perimeter using KVL. I encounter a plus 5 first, then plus 10, followed by a negative 20, followed by a plus 0, plus 30. Okay, so what happens is the overall is going to be plus 25. So this VAB is also the VC. Okay, VC, voltage across the equivalent capacitance, initial value, that is going to be plus 25 volts. Okay, pretty straightforward problem. So this completes series and parallel inductances and series and parallel capacitances.